Hello and welcome back to Data Analysis and Visualization. I'm Chivita Prithvi, and in this video, I'm going to talk to you about some more clustering algorithms. In my previous video, I showed k-means clustering algorithm. So in this video, we are going to see a couple of more clustering algorithms, just a brief overview of each of them. So let's begin. So the first algorithm is the kernel density estimation. If the k-means algorithm doesn't appeal to you, one alternative way to identify clusters in your data is to use a density smoothing function instead. So this is all about density smoothing function, where the points that you have, they are sort of merged together instead of being separated. Kernel density estimation, which is also called KDE, is just such a smoothing method. It works by placing a kernel, a weighting function that is useful for quantifying density, on each data point in the dataset, and then summing the kernels to generate a kernel density estimate for the overall region. So each data point of your plotting that you have done, that is summed up together to generate a denser and denser kernel every time, up to a point where you are left with only maybe 2 or 3 data points, which are your clusters. Areas of greater point density will sum out with greater kernel density, while areas of lower point density will sum out with less kernel density. So areas where there are more data points will have a higher density of kernels, and areas with less number of data points will have less kernel density. And because kernel smoothing methods don't rely on cluster center placement and clustering techniques to estimate clusters, they don't exhibit a risk of generating erroneous clusters by placing centers in areas of local minimum density. So like k-means clustering algorithm, it relies heavily on choosing centroids, and based on those centroids, the rest of the data points are classified into different clusters. Now, kernel density does not rely on these kinds of clusters, which is why it works very well in producing clusters which are not erroneous clusters created by placing centers in areas of local minimum density. Now, k-means algorithms generate hard-lined definitions between points in different clusters, but KDE generates a plot of gradual density change between data points. And for this reason, it's a helpful aid when eyeballing clusters. So it's going to generate a plot of gradual density change between data points. And here is an example. In one of my previous videos, I introduced to you this data set created by World Bank about income and children with primary school education. So percent of income earned by the bottom 10% of the population versus the percentage of children in that country who have completed primary education. So this is the graph of that, a scatter plot of that, and this is how kernel density algorithm works. You can see how certain data points are merged together to generate a denser and denser kernel. And in the end, all you can see is these big blobs of black, which show you data points that are merged together. So, for example, if you see here, this area is very dark black, which means this is where there are a lot of kernels, a lot of data points are together, and that's why it is a dense kernel. So this figure shows what the World Bank income and education scatter plot looks like after a KDE has been applied. And you can see that the white spaces between clusters has been reduced considerably because we are trying to merge things. And looking at the figure, it's fairly obvious that there are at least 3 clusters and possibly more if you want to allow for small clusters. So if you just look at the figure, you will notice that there are at least 3 clusters, and if you want more clusters, you could do that as well by just seeing how dense an area is and then classifying it as a cluster. Next, we have hierarchical algorithms for clustering. So just like we have kernel density, we have another algorithm called hierarchical algorithm. So this is yet another alternative to k-means algorithms, which we saw, and it results in a data set that's called a dendrogram. And here the top or the root is the entire data set. And then in each level down, there is a node where the data is split into 2 sets, usually of unequal sizes. And finally, at the bottom are leaves that each correspond to a single data point. So what you're doing is essentially you're doing almost something like KDE, but in this case, you're sort of creating a type of a tree, which is in this case known as a dendrogram. The root contains the entire data set. The leaves contain all the single data points, and then those single data points are merged together to generate a higher level. So that's why it's a hierarchical algorithm. You can use a number of different algorithms to build a dendrogram, and the algorithm you choose dictates where and how branching occurs within the clusters. So a dendrogram can be created by many algorithms, and based on the algorithm, the branching can be decided where the branching should occur and how it should occur. So this here, as you can see, is an example of a dendrogram. These leaves are all single data points. The root contains all the data, and the several nodes are combinations of several data points. So that's a dendrogram. In the example dendrogram that's shown in this figure, it appears that the underlying dataset has either 3 or 4 clusters. And how could we say that? Because it is built in a bottom-up manner, assembling pairs of points together and then agglomerating them into larger and larger groups. So it can be done bottom-up. It can be also done in a top-down manner by starting with the full data set and then splitting it into smaller and smaller groups. So if you just notice, let's slightly go back here. And if you notice, you can identify 3 separate clusters right here, or you could divide it into 2 clusters. It's up to you. So if you wanted to create more clusters, you could create more clusters. If you wanted less clusters, you could do that as well. Okay, let's continue. Hierarchical clustering algorithms are more computationally expensive than k-means algorithms because with each iteration of hierarchical clustering, many points must be compared to many other points. So computationally, they are more expensive in the sense you might need more time. Time-wise, it could be expensive. If you have a lot of data, then even the processing that is required could get expensive. So depending on all these things, hierarchical algorithms are more expensive because in k-means you're not trying to compare one point with every other point. You're just trying to compare one point with essentially the centroid, and then if the centroid is you just try to see if that point is closer to this centroid or that centroid and classify or cluster your data. But in hierarchical, you have to compare one point with all other points, and that's why it is expensive. The benefit, however, is that hierarchical clustering algorithms are not subject to errors caused by center convergence at areas of local minimum density. As you have seen in k-means that if there is a center convergence, then there could be areas of local minimum density, and that can be avoided in hierarchical clustering algorithms. Neither k-means nor hierarchical clustering algorithms perform well when clusters are non-globular. What is non-globular? A configuration where some points in a cluster are closer to points in a different cluster than they are to points in the center of their own cluster. So this is known as non-globular clusters, wherein there are points that have to be belonging to a certain cluster, and yet they are belonging to a different cluster. They are closer to some other cluster than their own cluster, than the center of their own cluster, and that's why the clustering gets all wrong. So k-means and hierarchical algorithms both will not perform well in case of such a data set. So then what is the solution? If your data set shows such non-globular clustering, then you can use neighborhood clustering algorithms. One such algorithm is dbScan to determine whether each point is closer to its neighbors in the same cluster or whether it is closer to its neighboring data points in other clusters. Now, this is nearest neighbor algorithm is something that I'm going to discuss in one of the future videos. So you'll come to know about that over there. So that is something that you can explore if you want to make use of hierarchical or k-means algorithms and it's causing you some trouble while clustering because the data set you are using is a non-globular data set. Now, this is an example of neighborhood clustering. So you can see points which are closer to each other are having a different color than the other ones. And you'll understand this better also because I have shown you already k-means clustering in with a Python code. So we saw this type of clustering being done over there. Now, what are neighborhood clustering algorithms? They are very effective, but they are subject to the following two weaknesses. The first weakness is neighborhood clustering can be very computationally expensive because at every iteration of this method, every data point might have to be compared with every other data point in the data set. So you have to, just like hierarchical, you have to compare one data point with another data point and so on. And because of that, they are computationally expensive. And with neighborhood clustering, you might have to provide the model with empirical parameter values for expected cluster size and cluster density. And if you guess either of these parameters incorrectly, the algorithm misidentifies clusters and you have to start the whole long process over again to fix the problem. So if you choose to use dbScan method, then you're required to specify these parameters. Parameters for cluster size and cluster density. So that there has to be some expected value of how big when you merge points together, then how big a cluster should be formed and what should be its density. So you have to provide this expected value based on which the algorithm will work. And if you incorrectly identify these parameters, then the algorithm is going to misidentify clusters and then you would have to start the whole long process again. Now there are two such ways in which you can do clustering. These are also very popular, like k-means algorithm, and that is one is decision tree. So at certain times you can get stuck trying to cluster and classify data from a non-numerical data set. So sometimes the data set could be non-numerical, and in time non-numerical means data which does not contain numbers but rather contains alphabets, characters like true or false values, or classifying something into high, low, medium, those kinds of things. So in times like these, you can use a decision tree model to help you cluster and classify your data correctly. A decision tree algorithm works by developing a set of yes or no rules that you can follow for new data in order to see exactly how it will be characterized by the model. But you must be careful when using decision tree models because they run a high risk of what is referred to as error propagation. And what is error propagation? It occurs when the rules that you provide are incorrect and errors are generated in the results of decisions made based on the incorrect rule. And then they are propagated through every subsequent decision that is made along that particular branch of decision tree. And I'm going to explain to you more about decision trees and how to implement them in the next video. So this video is only containing overview of all clustering algorithms other than k-means clustering algorithm. Now, to illustrate this type of an algorithm, consider that you have a data set which is often used in machine learning demonstrations, which is a list of passenger names from the Titanic. Okay. Now, using a simple decision tree model, you can predict that, if a person was a female or a male child with a large family, and whether or not he or she survived the catastrophe. So we all know what happened with Titanic, how it got drowned, and a lot of people died who were on board. And what we are trying to do is, we have this list of passengers, a list of passenger names, and we want to create a simple decision tree model where you can predict if a person was female or was a male child with a large family, whether or not that person survived or not, based on all these details that you have. So you can see here, these are sort of rules that you are feeding to your decision tree model. So what are those rules? First of all, was the person female? If the person was female, then directly you can assume that the person survived. Now, how? Because I think I don't exactly remember, but there was some sort of a provision made for females where they were allowed to get onto the lifeboats first. So probably if the person was a female, the person survived. So that's the first rule. The second rule, if the person was male, then there are two things. One is, what was the age of the person? Was the age less than or equal to 9 or greater than or equal to 10? If it is less than or equal to 9, then you are going to further check this rule, which says, what was the size of family on board, which means how many family members of that person were there on that ship. So if the person is less than or equal to 9, then you're going to check this. Now, if the family on board was greater than or equal to 3, which means other than that person, there were like 3 other family members or 4 or 5 family members, then that person most likely survived. So that's another rule. Then if the person was a male greater than 10 years old, then that person just died. That's what we are predicting. And also if the person was male, less than or equal to 9 years old, and had less than or equal to 2 family members on board, then also we are predicting that the person died. So these are the different parameters available to you, and these are the rules that you are basically feeding to your model. And based on that, now you would try to predict and classify or cluster your data. And lastly, we have the random forest algorithm. They are slower but more powerful alternative. Instead of building a tree from the data, this algorithm creates random trees and then determines which one best classifies the testing data. And it eliminates the risk of error propagation that is inherent in decision tree model. So random forest, instead of creating one tree, it's going to create many trees and then try to see which one of those trees is the best fit. So that way it reduces errors, and at the same time it gives you the best fit tree that is required, but it's also slower because it creates so many trees. So those are all the algorithms, all the options available to you if you want to perform clustering for your data. And in the next video, we'll see a little bit more about this and how to implement some of these. So I'll see you in the next video, and thank you for watching.